Hi, I'm Kunjian Song. In this video, I'm going to present to you ESBMC-Solidity. ESBMC is an open-source context-bounded model checker based on satisfiability modulo theories. ESBMC-Solidity is an extension of the original ESBMC to verify smart contracts written in Solidity programming language. Smart contracts are computer programs used in Ethereum blockchain. ESBMC-Solidity uses formal automated reasoning techniques to increase the confidence of smart contract developers, both functional and security. I'll start with motivations, then move on to the architectural overview, then a list of safety properties we currently support. After that, I'm going to show a couple of examples and how ESBMC Solidity was evaluated against other state-of-the-art tools. In the end, I'll present the future work as we planned, as well as the instruction of how to download and install ESBMC Solidity. So let's start with motivations. Smart contracts often suffer from vulnerabilities which can be exploited by malicious attackers. There have been two noticeable attacks in the past, caused more than tens of millions of monetary losses. One is the DAO attack in 2016. It resulted in a loss of $50 million. The other one happened in 2021. A hacker stole $31 million from MonoX Finance by exploiting a tokenization bug. So once deployed, there is no way to update a smart contract to fix the bug. Even the owner of the smart contract cannot modify it. It is critical to make sure a smart contract is secure before deployment. So here comes to our research question. How do we apply formal verification to ensure a smart contract is vulnerability-free? Our approach is to extend the existing state-of-the-art SMT-based model checker ESBMC. ESBMC can be extended to support different programming languages. So we developed a new Solidity front-end for ESBMC to verify smart contracts using the formal automated reasoning techniques that have already been implemented in ESBMC backend. We named the new tool ESBMC Solidity. So let's look at the architectural overview of ESBMC Solidity. Our verification flow uses the Solidity compiler, which is indicated by the gray box with a dash border, to pass the smart contract source code and produce the JSON abstract syntax tree. The new Solidity frontend is essentially a type check engine. It takes the JSON AST as input and performs semantic analysis on each AST node and generate the corresponding symbols. The symbols are fed into the goto converter to generate the goto program. The goto program is an intermediate representation used by ESBMC. The goto program is then fed into the symbolic execution engine, SIMAX, to generate the SSA form, the static single assignment form. Then the SSA form is converted into the verification condition, which is represented by the logical formula C and not P, where C represents the constraints and not P represents the negation of the safety properties. Then the logic formula is solved by an SMT solver, for example, Z3, to find the satisfiability. If the formula cannot be satisfied, then it means the smart contract is safe up to bound K. ESBMC will report verification successful in this case. Otherwise, ESBMC will report property violation and a counterexample with a state trace. So let's look at the safety properties currently supported by ESBMC Solidity. The safety properties are based on the SWC registry, the Smart Contract Weakness Classification Registry. We are currently supporting the detection of integer overflow, integer underflow, authorization through TX origin, and out-of-bounds access in both static and dynamic arrays. In addition, the user can instrument the code by adding function hooks. ESBMC assume can be used to add additional constraints. The non-det function provides non-determinism. For example, it can be used to return a non-deterministic 8-bit unsigned integer between 0 and 255. I'm going to present a couple of examples to show how ESBMC Solidity can be used to verify smart contracts, detecting bugs in the source code. The first example is pretty straightforward. Let's say we want to verify the smart contract on the left. Here we have a smart contract that contains a state variable x. Within the function, we would like to verify x is initialized to 1. After this point, x was decremented twice. At the end, we would like to verify the value of x is less than 5. The command line above it indicates arguments to invoke ESBMC. What we have here is the ESBMC binary followed by the JSON EST file generated by the Solidity compiler. The dash function argument tells ESBMC which function to verify. We use the contract argument to provide the source code. The compact argument tells ESBMC to print state trace. As you can see, the screenshot on the right, ESBMC was able to find the integer underflow bug in the smart contract being verified. So the next example shows the detection of integer overflow. In this example, we have three state variables that are initialized in the function func_overflow. The sum of three numbers are calculated in line 15. However, the value actually exceeds the limit an 8-bit unsigned integer can represent. So we have an overflow problem here. The command arguments we used in this example are pretty much similar as in the previous example. Again, ESBMC managed to detect the integer overflow bug in this example. So the next example involves a static array in the smart contract being verified. Here we have a static array A declared to have just two elements. The first element is initialized to 100, followed by a for loop populating the remaining elements. However, the condition in this for loop exceeds the boundary of the array. And the ESBMC successfully detected the integer, the auto-bound access in static array. And this example shows the verification of dynamic array. Here we have the function we would like to verify. This function takes an integer as parameter. Within this function, the function parameter will be used to declare the dynamic array A, representing the size of this array. The for loop is used to initialize each element of the array to 100. At the end, we assert the first element is equal to 100. The array initialization in this function works fine with non-zero positive integers. However, if we give 0 to this function, it would fail with auto-bound access. ESBMC managed to detect this bug in the function and provided the counterexample indicates if the size was 0, we would have an auto-bound array access. As you can see in the command line above, we also have an additional argument, --incremental BMC. This is the verification strategy we use to verify this example. It means incremental loop unwinding verification. In the last example, I would like to show you how the user can instrument code in ESBMC-Solidity. This is a nice feature of ESBMC. So apart from the default safety properties supported, the user can also instrument the code by adding additional constraints using the function hooks. For example, the nondet and ESBMC_assume functions. They are the function hooks that allow the user to instrument the code. Within the function we would like to verify, the func_set function. We have three variables, x, y, and sum. X was initialized to 0. Y is a constrained non-deterministic value between 0 and 255. Sum is just x plus y. So we would like to make sure sum is not a multiple of 16, indicated by the assert statement in line 28. In between, there are a bunch of constraints added by the user to put a range on y, which is between 220 and 255. So within this range, there are two values that can violate the property we want to check. So there are two values being multiples of 16, but variable y is further restricted to avoid the number 224, which only leaves 240 being the value that can violate the property. Again, ESBMC managed to detect this value. If the user uncomments line 25 to put a further restriction on variable y. To avoid 240, ESBMC would report verification successful because there would be no value within this range that can be a multiple of 16. So no satisfiability exists in such case if the user uncomment line 25. Let's look at the experimental evaluation. Since there's no official benchmark for Solidity language, we created a small test suite that also includes the examples in the previous slides. The test case design was based on SWC registry. We compared ESBMC with some other state-of-the-art smart contract verification tools. Looking at the result table, column found indicates whether a bug was detected, followed by column CE indicating whether a counterexample was provided. The total time represents the CPU time used for verification. So overall, ESBMC-Solidity shows the best results, reporting bug found in all test cases faster than the other tools. ESBMC-Solidity was also the only tool, was the only tool that successfully provided a counterexample for each applicable test case in our experiment. Although ESBMC-Solidity is an early prototype, it shows promising results. Our current focus is on extending the new Solidity frontend to cover 100% Solidity grammar production rules and data types. In the future, we also plan to add support for to verify OOP features such as polymorphism and inheritance. We also want to add support to verify EVM memory management, for example, the usage of keywords, storage, call data, and memory. We also plan to add support to verify special features of Solidity language, including multiple returns in a function and some crypto functions, for example, keycheck 256 and SHA-256. We would also like to improve the extendability and maintainability of Solidity ESBMC Solidity. For example, investigating the usage of shared libraries in a Solidity compiler to avoid maintaining Solidity front-end manually. To download and install ESBMC Solidity, please follow the link in esbmc.org. Thank you very much for your time.